this guy.
Thank you.
Thank you.
Good morning. We have another short presentation on the general framework of the ground motion logic trees that we'll be going through how we're going to flesh those out in the rest of the presentations this morning. So the basic steps that we are, as Doug went through yesterday, that we're going to be using to build the logic trees is that we will select a set of candidate GMPEs for specific seismic source categories. And so we've grouped the contributors to the hazard at the two sites into 4 categories based on the results of sensitivity analysis that we've seen up to date. For Diablo Canyon, we have a nearby 5 to magnitude 8 strike slip earthquakes, and the second category would be the nearby 5 to 7.5-ish roughly reverse faults on the hanging wall. So specifically, the site Diablo Canyon sits on the hanging wall for those types of sources. So those are the 2 source types for Diablo Canyon. For Palo Verde, we have 2 source types also. We have normal faulting in the distributed zone around the site with no specific nearby faults identified. And we have a distant magnitude 7 to 8 plus 8-ish plus strike slip earthquakes in California that are contributing to the hazard. So they have, again, 2 source types for, or source categories for Palo Verde, and our basic concept is we will build a logic tree characterization for all 4 of those source types. The process will be to select the appropriate set of what we consider to be appropriate set of candidate models for ground motion models for evaluation, develop distributions of possible models through parameter sampling that Nico just talked about, and I will talk about more, by refitting the sample space of these refitted ground motion prediction equations, develop a discrete representation, a limited number of weighting models using comparisons with data, models, simulations as appropriate. The set is nominally, right now our working hypothesis is about 10, but ideally we will select the minimum number we need to represent the uncertainty properly. These models may include some specific adjustments for specific source effects as needed, in some cases directivity or specific source or path effects. And then we will develop a separate characterization of aleatory variability, which is appropriate for the specific source category being evaluated. These are a list evaluation of the set of candidate models that we consider at this point appropriate for use in evaluating the different source categories. And if we're looking for the particular cases for Palo Verde, we have for normal faulting, it's primarily the NGA West 2 models plus the European models that specifically had a lot of information on normal faulting, the Akhar et al. And Bindi et al. Models. Bindi we consider to be appropriate because the primary focus is on earthquakes of magnitude 7 and less, where the issues with their high magnitude scaling are not important. Some of the other models, such as Idris or Zhao et al., didn't specifically evaluate normal faulting earthquakes. And then for the distant strike slip earthquakes, we will be looking at, again, pretty much the same set of NGA models, and we will be basically making it a comparison with the distant data from Arizona in terms of the rate of attenuation to select models that are consistent with that attenuation as our starting point. So this is the basic form of the ground motion logic tree. This is for the distributed normal faulting earthquakes in Arizona. We will have potentially multiple evaluation sets of appropriate data. The data set would be data from the NGA data set, but we may potentially get access to data sets from Europe that went into the European models that may provide additional data for use in evaluation. Then we will develop our suite of ground motion models, nominally shown as 10 on this slide, and then develop weights on those models based on evaluations of relative likelihood, mean bias, comparison with the ground motion, the underlying equations, the information, the discussion we had yesterday, and which we still have to work through. Then in terms of the normal faulting events in the random host zone, we do not at this point envision any specific need for special additional effects such as directivity. We're dealing primarily with randomly oriented smaller magnitude events without specifically identified fault sources. So the issue of directivity is probably not important for those. And our vision at this point is to deal with, because we will have sites on both the hanging wall and foot wall of these randomly oriented faults, that we will explore primarily characterizing the ground motion distance equation for these in terms of joiner bore distance rather than trying to deal with explicit hanging wall effects for these smaller events. And then we will be developing aleatory variability models. Possible differences could be magnitude dependence or magnitude independence, and then which will be basically evaluated based on model-to-model variability. And then finally, the estimates of the actual aleatory variability values would come from, again, model-to-model variability as well as statistical uncertainty in actually estimating the values of tau and phi. So, and then for, oops, I lost the bottom. So this is for the distant strike slip faults. Again, we will potentially have multiple data sets. In this case, we would have some large magnitude data at distance, but we also may be using data sets for evaluation, which are the smaller magnitudes, which are not relevant for the size of the earthquakes that will be affecting the site, but they are relevant for evaluating the path rate from attenuation from California into Arizona. Again, the set of models would be developed. There may be specific path adjustments that we'll evaluate, such as maybe differences from the northern Mojave sources compared to the southern Mojave sources and the Salton Trough. If there are path adjustments, we may have statistical uncertainty in those. So there may be alternative path models, again, depending on the results of evaluations. The aleatory variability form will probably be magnitude independent because we will be dealing with a relatively narrow magnitude range that is large magnitudes. So we will not, the contribution to hazard from events smaller than 6 at those distances will be, is insignificant. So we do not need to deal really with magnitude dependence in sigma. And then again, uncertainty in the actual estimates of the values of the aleatory variability terms. So that is the general framework we'll be using. Are there any questions?
So, Bob, for the Idris, 200, 300 kilometers, I don't know if it's really applicable. I know
we will have to, again, we'll be evaluating how it compares with the attenuation we see in the data from Arizona.
But if the author says no, because I was in communications, even 200 kilometers was a little bit a stretch, but USGS accepted that.
We're doing an evaluation. Ralph.
Bob, you mentioned on, I think it's the next slide, that yeah, here. I mean, if there are no nearby faults where you don't have to worry about directivity, then why would you even consider the hanging wall effect if you're not close?
Because there will be earthquakes close by. They'll be smaller.
Okay.
And we'll be on. I mean, the source will include earthquakes at all distances, all the way up to the site. There are just no specific faults they're associated with.
Got it.
So they'll be randomly oriented with dips in typically around 50, 55 degrees. So it's not expected to be a big impact, and so we will be on the footwall and the hanging wall side of those. And so I think the evaluations have indicated that joiner bore distance works reasonably well for those types of sources, and so we may just use joiner bore as the distance measure to deal with that.
Got it. Thanks.
What is the schedule on these things? The schedule on this?
Soon.
Very, very quantitative.
Not this week, but soon.
Our schedule is to be complete with the model in July.